You are listening to EETimes on Air, and this is EETimes Current. I'm Taylor Marvin. Welcome to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this episode, we hear from key technical people at the Southern California-based AI hardware company BrainChip. Your hosts are Dr. Sunny Bains of University College London and Dr. Giulia D'Angelo of the Czech Technical University in Prague.
Welcome to Brains and Machines. I am Giulia D'Angelo.
And I'm Sunny Bains.
In today's episode, Sunny talks to 5 of the engineers and computer scientists working at BrainChip, including the company's Chief Technology Officer, Dr. Tony Lewis. There are links to their work and some of the specific papers we will be discussing on our website. You can check them out at brainsandmachines.net. After the interview, we will be talking to Ralph Etienne-Cummings from Johns Hopkins University about the issues raised.
Thanks, Giulia. BrainChip is based in Laguna Hills in Orange County and is probably best known for its Akida chip. Today, we'll look at the company's business strategy, their new flavor of neural network intended to run at the edge, including both how it works and what results they've had, as well as providing a little insight into their strategy with their next iteration of chip. In AI terms, BrainChip is a relatively old company. It was founded by Peter van der Made in 2004 to commercialize neuromorphic devices and dynamic learning. He was joined by Anil Mankar in 2015 as Senior Vice President of Engineering. Both have now stepped down, and at the end of 2023, Tony Lewis was brought in as the Chief Technology Officer.
The company was primarily doing research, so trying to figure out what is the best way to take ideas from the brain and put them into devices. And then at some point, about 2 or 3 years ago, they began to think about commercialization and how to take these ideas to market in the form of IP or intellectual property. What does that mean? That means if you wanted to build a chip, you need to have the underlying design to build that chip. And so you might go to a number of vendors for parts of that design. One part that we would provide would be the neural processing engine, that neuromorphic engine that would allow you to execute AI workloads. And so the model of the company is that we sell or we license this IP to people who are building chips. Occasionally, we fabricate our own chip to convince ourselves that our IP is good and that it performs as we think it should. But primarily, the way we make money is by licensing IP.
For the last 10 years, the focus of the company has been consistently AI at the edge. BrainChip has particularly been working on processing signals with a temporal dimension on tiny, low-power devices. Applications can include anything from large language models and speech recognition to eye tracking, gesture recognition, and noise suppression for hearing aids. Tony Lewis explains that standard neuromorphic approaches use networks as long short-term memories, or LSTMs. These can be sped up and made more efficient using recurrence, but that's not always straightforward. BrainChip has developed something called temporal event-based neural networks, or TENNs, that he says solve many of the problems that arise.
So recurrent networks are wonderful because they can represent a problem in a very compact way with very few weights. Their difficulty is that they're really difficult to train. They're unstable, they're unfriendly. People would rather be in the convolutional domain. But when you go to the convolutional domain, suddenly you're doing a lot of computation each time you want to come up with the next inference. The breakthrough in state space methods is that you can now train recurrent networks, just like an LSTM, in a very stable way. You can convert between a convolutional domain where things are easy to train, and you can fold it into this recurrent domain where you can run really fast. And so you get the best of both worlds, stable training plus a very compact size. And so what's inside this recurrent neural network? You have this thing which is essential. It's a state. What is a state? It's a summary of everything that has come before and that the network has been exposed to. And in terms of a TENNs network, this could be virtually all of time that has come before. So it can listen continuously. It doesn't have any limits as to how long it can listen. And so this state is a complete and compact summary of everything that has gone before. And the network uses that state plus incoming information to make its next prediction. And as a result, we end up with networks which are far smaller, a small fraction of the size of a convolutional neural network. And remarkably, they also behave much better. One of the reasons why they may behave much better is that the networks have a physical basis for representing the world. So why is that important? A traditional convolutional neural network can represent anything, even things which are not physically possible. And so as a result, they take a lot more training data to train. They take longer to train. But if we confine ourselves to things which are physical, like audio signals or cars moving around on a freeway, we can come up with a solution which trains much faster with less data.
Dr. Jan Pei, known as Rudy Pei, is a research scientist at BrainChip and one of the inventors of TENNs. I asked him to start by explaining what was the difference in the way these networks deal with time.
So temporal neural networks, or TENNs, are basically neural networks that can leverage long-range temporal dependencies. And basically, a wide range of tasks nowadays requires long context. One popular example being large language modeling. So when humans, they read a novel, they have the back of their mind sentences or paragraphs from a long time ago, or even the previous chapter. So to establish this sort of long context, you need a model that can basically sort of memorize the past or compress the history of the past in a very intelligent way. So large language model obviously being the most popular one, but even for audio processing or any signal processing in general, you require some sort of historical context. So really the goal of the network is to leverage context to make intelligent predictions based on temporal correlations in the past.
These applications are both sound-based, and so essentially one-dimensional. However, Rudy Pei says the network is particularly efficient when it comes to the kind of 2D tasks required for vision. This is important because they tend to scale very badly in traditional networks.
So traditionally, in order to perform temporal, let's say, convolution, you have to buffer all the previous frames. So let's say you want a context of 30 frames, then you literally, at each layer, you have to buffer 30 frames, which gets magnified by the spatial dimension. So obviously, this is not a very edge-friendly way to approach it. So in our TENNs network, we have I guess we can think of it as an intelligent online compression of the historical frame. So we don't actually have to explicitly buffer previous frames. It's more like a continuous compression of the historical context into a single spatial temporal feature. So it's much less memory bound in our case.
Key to the working of these networks is the way time is represented using Legendre polynomials. These not only make the networks more efficient, but also more representative of physical reality.
So Legendre polynomial is derived from a set of physical differential equations. So let's say if we want to approximate the past trajectory of the car, we can sort of project the trajectory into these orthogonal polynomial bases. So the coefficients of these polynomial bases basically forms a very minimal compression of the previous continuous trajectory of the car. So we chose Legendre polynomial precisely because there's an underlying physical system basically describing it.
We're not going to get deep into the maths here. You can look at the technical papers for that. But if it helps, which it does for me, you can think of these polynomials as being somewhat analogous to the Fourier transforms that are used in signal and image processing.
Yeah, exactly. As you mentioned, spatial pattern can be compressed using 2D Fourier transform. So in the temporal dimension, you can technically also use FFT or Fourier transform. But Legendre polynomial is related to Fourier transform, but it's like a generalized version of it. So one way I like to think about it is that it's a Fourier transform with a certain physical basis. I guess one popular application for this is object tracking. So one of the common problems with autonomous driving, let's say, is that we call them ghost vehicles. So suddenly you have a bounding box around a car and then the car just disappeared in one frame and then reappear again. So this is obviously not abiding by physical law. One of the important points of having this temporal continuity is that you want to consistently track the object in a very physical manner. The car has a certain limit of acceleration and jerk based on some physical inspired algorithm that is baked into TENNs. We can make spatial temporal prediction that abides by continuity predictions. So self-driving, object tracking, and many computer vision tasks in general can benefit from this sort of temporal consistency.
Tony Lewis points out that what's cool about this is not just that it can be done, but that it can be done in a way that doesn't involve fiddling with the results after they've been obtained.
In the TENNs approach, this is based into the basic architecture, versus maybe other approaches people might use would be to first detect an object and then put that into some sort of mechanism that maintains continuity in sort of an ad hoc manner. So the TENNs approach is, in my opinion, much more elegant and complete.
One of the key concepts in temporal processing is causality. Essentially, this has to do with how much data you have to gather and process before you can make predictions about the future or categorize the past.
So causal basically means that the current prediction only depends on the current input and all the previous input. So the reason why it's important is because for a low latency non-causal system, the current prediction has to depend on possibly future frames as well. So in terms of edge system, this means that you have to wait until you gather all future frames to make a prediction in the past. So causal, I think, is a cornerstone of online inference system. So if any system has any hope of being deployed on the edge or being efficiently online inference compatible, it has to be causal. So I guess one example would be most popular ASR system like conformers and wave-to-vec2. They're a popular ASR model. ASR is a task of converting audio into speech. So they basically have to listen to your whole speech first before they make any prediction. Even the first text has to depend on your entire speech. So that is a non-causal way to do things. Whereas for causal models, as soon as your speech token has finished, it can make the correct prediction based on whatever it has heard. So as I'm speaking, it's like a live transcription kind of thing. And if the model is truly causal, then the live transcription will have a theoretical latency of 0. So as soon as I finish speaking, the live caption would pop up. So that is the end goal of the causal system. And I think ASR is a good example of the distinction between the two modalities, essentially.
Of course, as with everything, there are always trade-offs to be made.
I see causal and non-causal is more like a spectrum. In theory, there's no pure non-causal system or causal system. It's more about how far you peek into the future. Of course, if you finish listening to the human speak, first you have more future context, you'll be able to make better prediction. And that is the fact that it's commonly being observed in the literature. So it's really like a balance of how low you want the latency to be and how accurate you want the prediction. And if you plot it on the graph, it's like a Pareto frontier. So basically, the TENN network is sitting at the frontier of the curve, meaning that for both causal and non-causal application, we will be expected to outperform the counterparts. It's what we hope to achieve. We already achieved it in the causal domain. We're trying to push it to the non-causal domain as well.
As we discussed back at the beginning, recurrent processing is also critically important to the BrainChip approach.
So the difference between a recurrent network and a typical, let's say, convolution network or a feed-forward network is that a traditional neural network or a feed-forward network does not contain internal states. So the internal state can be considered as like a memory of the network. So what happens is that if you feed the data to the system, the network will intrinsically memorize what it has seen in the past in a very abstract, compressed states. So each layer of the network contains an internal state, and that is the traditional recurrent network. I guess one thing I should mention is that traditional recurrent network, the recurrent mechanism is nonlinear, meaning that during training, the backpropagation also has to be sequential. So the forward inference is sequential based on the recurrent update structure itself of the system. So that basically induces like a backpropagation that is also sequential. So that is why it is poorly supported on modern GPU hardware. And one advantage of TENNs is that we don't actually suffer from this sequential sort of blockade, because we emit like a parallel form for our network. So in some sense, I guess our network is a recurrent network that can also overcome the limitations of traditional nonlinear recurrent networks.
Dr. Olivier Coenen, senior research scientist at BrainChip, worked with Rudy Pei to create the temporal event-based neural network. He gets deeper into its operation and where it saves on resources.
So in our case, if we're talking about TENNs, we have a recurrent form and a buffer form. So in the recurrent form, what that allows is to decrease the amount of memory that you need to store all those weights. Usually all the weights, the kernel weights, convolution weights, it needs to be loaded and to be available in memory. While in recurrent mode, you only need to have in memory the current state and the actual local little weight that is necessary for the next iteration. So that size is much smaller. And so it allows to do the same type of computation, but with smaller size, essentially network in memory. So recurrent neural networks came along and they were great and they're especially very good for inference. But then training was really slow. And then Transformer came along and said, here, we have a system that basically does the job of RNN, but we can train at least 10 times faster because they could use parallelization in training. And then we're using transformers. But the problem now is that you need a lot of memory. And with our system, you can actually train like a transformer or CNN using all the parallelization but then you can transform it into a recurrent neural net. And the advantage is that you can basically have your cake and eat it too, meaning that you can train very efficiently and then at the end of the day transform it into a recurrent neural network, which is a lot more efficient in terms of memory. And so that means that we can have a much smaller footprint.
Mamba is another relatively new model that's good at processing temporal data. I asked Rudy Pei how it compared to TENN's.
So Mamba is basically like another line of research that happens concurrently with the TENN's research as well. And obviously we take inspiration from Mamba as well. But I guess the core difference between Mamba and TENN's is that Mamba uses internal state as well, but their internal state is actually expanded. So meaning that they do have a very large internal state bank. So this is very good actually for GPU inference, obviously as proven. The recent popularity, they can do large language modeling very well, especially for hybrid models due to their large internal state bank. But one of the disadvantages is that this is very poorly supported for edge inference because you have to maintain all of these large states and you have to continuously evolve them, which is not amenable for lightweight compute. So the major difference TENN's is that we do have a very small compact internal state bank, so that can be very easily maintained on chip. So to be a little bit technical, basically the internal state bank can live directly very close to the processor so that it can be fetched data and continuously updated very fast. So I guess that's the core difference.
In effect, it's not that TENN's is necessarily better or worse than Mamba, it's just different.
So we don't know for sure, but we believe that Mamba and TENN's both have their respective domain specialty. Maybe TENN is better for certain tasks like audio. Maybe Mamba is better for certain tasks like large language modeling. We're actually not sure. So obviously these two models will continuously evolve and they'll continuously push the Pareto frontier. So we think in the future, TENN's possibly can do large language modeling very well, as we recently proven as well. So I guess I cannot make too rigorous comments on like exactly the domain that they're good at. I don't think there's a very fluid boundary actually between the two, so it's hard to say.
Tony Lewis says, though both are still new, the likely sweet spots for each are starting to emerge.
As Rudy mentioned, these are two parallel lines of research. Rudy and Olivier, they began this TENN's research about 2 years ago, and they were getting good results. And so we were able to create underlying hardware which could run these networks very efficiently. And so there's been a continuous evolution or co-evolution of both hardware and the algorithm so that we get good performance at the edge. Whereas I believe we can characterize Mamba as something which is recently targeted at the GPU hardware, which has some optimizations for GPU hardware, etc., which don't really translate very well to edge use cases. So one view is that we're more tuned to the edge use case.
One important area that they're looking to commercialize is large language models on the edge. This is where the comparison with Mamba becomes interesting.
So we basically benchmark TENN's against popular state-space model network. So there's two flavors of Mamba now, Mamba 1 and Mamba 2. We basically outperform Mamba 1 and also the transformer models like Tiny Llama or Llama 3.2, basically up to 1 billion parameter regime, so with much less parameter. So I think we're very confident that this sort of approach can push the boundary of lightweight, small language modeling, I think. We thought originally that TENN's could not perform language modeling super well due to their small internal state size, but it turns out that once you have a very good enough physical inductive biases for compression, you can get away with large language modeling with small states as well. So that was one of the results that kind of surprised us, that we were able to outperform Mamba.
Among the underlying concepts behind the efficiency of the BrainChip approach is the use of events and the sparsity they provide. Tony Lewis points out how important it is for us to remember what events and spikes are, and that they're not the same.
What's the difference between an event and a spike? A spike is usually defined as a single value, either the appearance of something, a one, or non-appearance. An event could also carry information additional to that 0 or 1. It can carry the activation level, say, of a previous neuron. So we look at our hardware as event-based hardware. And where does it excel? Whenever we have both weight sparsity and or activation sparsity. So where perhaps the output of a neuron after it's done with this computation, it computes 0. And so this 0 is never forwarded, it's never sent to the compute engine for processing. And so we naturally save some compute power when we have sparse networks. When we look at Rudy's networks, when we look at any sort of TENN's network, we do see a great deal of sparsity. And we're trying to figure out ways of increasing the sparsity so that they run very efficiently on our underlying event-based hardware. So there's a distinction between pure spike base and events. And then it just happens that the TENN stuff is sparse, which is fortuitous for us. There is a formulation of TENNs which can digest just pure spikes, just zeros and ones as well. And so there's a lot of theoretical foundation behind it. We've been able to show that we can do some interesting things with event-based cameras. For instance, digesting the outputs of event-based cameras for eye tracking, for gesture recognition, et cetera, where we achieve incredibly good results, better than other researchers who have experimented. Without getting too far into the weeds, we can digest either analog signals, we can digest words, we can digest events, all using the same framework, which is TENNs.
Dr. Chris Carlson, manager of applied research at BrainChip, explains how the sparsity that we've been discussing works within the system.
We have these things called neural processors, and then we have a mesh that communicates events to these neural processors. Each one of these neural processors has 8 engines. And these engines, each one of them has a different set of weights to process this event with. So again, picture a single event coming in to my neural processor, and then I've got some set of neural processor engines. They each look at that event value, but then they each apply a different set of weights to that event. And so that's how you're parallelizing things at the event level. But the real benefit here is the fact that the events that they see, those are already only non-zero activations.
This is a big advantage. There's less information to process. But the way the parallel computing is done has to take account of that.
The reason this is the case is because a lot of times when you're trying to parallelize things, what you want to do is you want to group everything in a very organized way, and then you want to just chunk through it as efficiently as possible. However, when you're trying to take advantage of sparsity, you have a little bit of an overhead for parallelism in some ways, right? Because the idea here is I want to allow myself to compute basically the minimal amount possible. And that necessitates that you look through or basically communicate only when you need to. There's no way for most of the designs that are massively parallel, there's no way to be able to say, oh, just do this a little bit, right? Because that means you have to have some sort of logic there to choose that. And there's an overhead for that. So of course you don't want to be able to do that. So you want to order your data in a very specific way so that you could just crunch through it all in one go. Where with sparsity, you want to be able to say, oh, actually this whole area, I don't even have to look at it. I'm just going to skip it or something like this. So that's why at a design level, they could be at odds.
I wondered whether this suggested that it wasn't the parallelism that was the problem, but rather the fact that the processing was fixed and couldn't adapt to the changing input.
Exactly. That's what I mean. It's perhaps the data ordering or the way that you're crunching through things. That's why I said the data pipeline is perhaps too fixed, so you can't choose subsets of it. So it's not exactly parallelism. It's more, you're right, these things that don't allow you to choose things. You just have to do them all at once. So you're right. I think that's true.
Oliver Koenen expands on this.
In many systems currently, you assume that you have a certain size of data, and then you try to process it as efficiently, as quickly as possible. And basically, the only thing one can do is chunk it in parallel. While on the other extreme is that you assume that you don't always have the same size of data, and then you are trying to minimize the number of operations. And so therefore only process the ones that are active. And so therefore using sparse activation to determine what you're going to be processing. And so it's true that even in the sparse system, you can use some level of parallelization in order to process the ones that are active. But I think the main point or idea at the first was that these systems were developing. Parallelism was the only thing that could help and make them advance and process faster. Well, we have two things that we can do, right? In our case, with like an Akida system, is that we all have at some point, we have level of parallelization we can use. It's always there, but it will also have sparsity. In other words, only focus on non-zero activation in order to be more efficient.
Tony Lewis says he's excited about their recent results.
So I've been here for a year, and so I've been observing Rudy's progress of others. And what's surprising is we pick disparate fields and we get excellent results in a very short period of time. We aren't experts in eye tracking, but we competed with an open competition, and in a very short period of time, we beat everyone in 4 out of 5 categories. So that was surprising. And we don't know anything about eye tracking. We don't know much about audio denoising. We put together a network, a pretty innovative network, which is built upon the TENN's building blocks. And we got incredibly good intelligibility scores, but at a small fraction of the size and compute as existing state-of-the-art networks. We then looked at ASR and really put together something that within a very short period of time, we were getting really competitive automatic speech recognition results with excellent word error rate. And we had a perfect score on our gesture recognition. And so what's interesting is we have this tool which allows us to get incredibly competitive results without being domain experts. And so for me, that's surprising and shocking, at the same time. But we seem to do it again and again on a very regular basis.
Chris Carlson says their experience with eye tracking has been especially illuminating.
So the idea is you have an event-based camera and you're trying to track someone's eye. What we found with our TENN's model is it did spatiotemporal convolutions, basically a 3D convolution over space and time. And it had a bunch of these spatiotemporal blocks. And remember, this thing is event-based, so it's sparsity aware. What we found was we entered into this, I think it was a CVPR 2024 competition, and I think we got third place from an accuracy perspective when I think the threshold was if you allow for 10 pixels of error, then I think we got third place. But what we found was if you allowed for 5 pixels or 4 pixels or 3 or 2, we did better than everyone. So this thing was really accurate. And the really interesting thing about this model was that when we added activity regularization, which basically helps you induce activation sparsity, we found that we basically lose very little accuracy. So the ability to track accurately one's eyes, even when we get up to sparsity, that's around 90%. Okay. And so what's really nice is that if we had no sparsity in the model, you would, I think, do 55 million max per inference or something like this. But if you have sparsity, you're doing like 5 to 6 million max per inference.
There are also many other markets where Carlson sees potential.
So a lot of the things from an application standpoint that I'm interested in and excited about are basically streaming data at the edge. A few examples of this are something like audio denoising, where you have noisy audio coming in and you want to have clean audio coming out of your system. Something like keyword spotting or wake word, and you're listening to streaming data very efficiently at low power. So some of these other things, of course, would be vision applications that, again, are streaming. So picture some sort of security camera or something like this, where now you're not processing individual frames. Or another just quick one off the top of my head is like wearables for health monitoring and things like this, right? So maybe you're monitoring heart rate or any type of biological signal, but you can picture that as a system of 1D time series. And you might want to be able to find some correlations or do some regression or whatever. But you could do this really efficiently with our temporal event neural networks.
I asked Tony Lewis whether he agreed that biomedical applications would likely be important.
If you have anything that's wearable, anything that's battery powered, then power or energy is at a premium. And so when we see a reduction by 1/10 in the power usage for equivalent or better performance, it suddenly makes this new flavor of neuromorphic engineering incredibly attractive to the biomedical field. And I can't guarantee it, but based upon our previous experience, we think that we would do extremely well in this field once we start developing algorithms, once we've identified partners. Because as you know, Sunny, if we're going to be good at this field, we require someone who has the data and the vision for how this would be used. We're merely IP providers and purveyors of incredible algorithms. We need those partners to effect a change on society.
Although they are mainly providers of IP, they do also, as the company name suggests, have a chip called Akida. I asked Dr. John Tapson, Chief Development Officer and Vice President of Engineering, what their plans were for future iterations.
At BrainChip, we are currently finishing off our Akida 2.0 architecture. And this is an expansion on all of BrainChip's prior work. It's essentially a neuromorphic chip. It's event-based. It makes use of the intrinsic sparsity in signals to achieve high levels of efficiency. But we have the same problem at any company that does there's an enormous difference between research silicon, if I can put it that way, and commercial silicon. And the problem with commercial silicon is you've got to fit in the ecosystem of what everybody else is doing. The kind of history of startup companies is littered with companies that had fantastic technology but couldn't progress across the interface to regular technology. And the real problem is if you build a chip, the chip by itself is not a solution to anything. It's got to go on a board. It's got to have a software ecosystem around it. And the easier that is for customers and engineers to access, the better everything's going to go. So I think that a big part of Akida 2.0 is it's got some fun things. It can operate at multiple different scales of resolution. So it can operate at 8 bits, it can operate at 4 bits, and it can operate at a single bit resolution. And that's actually a very interesting thing because if you look at the trend in edge and neuromorphic processors, its spikes are intrinsically 1 bit. And then a lot of people realized that to actually move a spike around a circuit takes a lot of signals. So you think of a spike as a 1-bit signal, but by the time you put an address and a bunch of timing information, there's 19 or 20 bits of information actually being transmitted. So if you're going to take 20 bits to send a single spike, you might as well add 4 more bits and send something which has amplitude rather than just being binary yes, no, spike presence. And then you might as well send 8 bits because that's only another 4 bits kind of thing. And I think in the field, there was a real reluctance to move away from the binary spike idea because that's actually the core dogma of neuroscience. And just as an aside, I thought a lot about something that was said by Rodney Brooks, who's the great roboticist. I think it was an advice to young academics thing, as he said, choose the central dogma of your field and ask yourself, what if that dogma is not true? And you think, okay, what's the central dogma of neuroscience? And one of the central dogmas is a spike is a spike. The shape of the spike carries no information, and the amplitude of the spike carries no information. The only thing that carries information is that it happened at a certain time. And so you say, okay, what if that's not true? And there's been a huge reluctance to move away from that dogma. Neuromorphic engineering as a field was tremendously committed to the idea that spikes were spikes. And then you find out that actually, you know what, I can send a value and I have a much richer range of algorithms, and it doesn't cost me much at all in the circuitry. So you get this kind of reluctant move from 1 to 4 bits, and then you say, what the hell, I might as well go to 8 bits. And just foreshadowing, our next architecture is going to be 16-bit without a question, because it just opens up a tremendous number of algorithms. And then the funny thing is you actually see the big guys, as NVIDIA, for example, moving the other way. They had a massive commitment to 32-bit floating point, 16-bit floating point. And now suddenly they're offering 8 and 4-bit operation as well. So they're converging in the opposite direction. We're all converging to 4 and 8-bit values. So I find that very interesting. And that's one of the nice things about our new architecture. And then just one of the big optimizations that you make when you make a neuromorphic chip is the extent to which it's just a state machine. So just a bunch of electric connections that are hardwired. I think hardwired is the key phrase there, to do a task. And then the extent to which it's actually programmable. And at the neuron level, you have a little bit of programmability. You can maybe change output functions or change flow control or something, make simple sort of if then else type decisions at the level of a neuron, at the level of a data passing through a neuron. And again, I think there's a well-established trend where as a neuroscientist, you kind of think, well, this stuff is hardwired. You know, the brain doesn't run microcode. It learns, but it learns by changing its circuit. And therefore, we electronically should be learning by changing the circuit. And then you realize that we're neuro-inspired, but not neuro one-to-one copying. And it's not a bad thing to have some programmability to give you just the versatility to run a bunch of different workloads.
I wanted to end with a vision of the future of neuromorphic engineering and of BrainChip. Tony Lewis gives his perspective.
So right now, what is the point? What is the overall point of neuromorphic engineering? And what is the right level of abstraction to take ideas from the brain? So I think that's something that needs to be teased apart. I think Carver Mead's original idea was that we can look at the underlying physics of silicon and we can see some parallels with the human brain. So this is a tremendous insight. What we have is a digital framework which can be fabricated with standard technology, which doesn't require anything exotic. And it may require a different level of abstraction when we borrow ideas from the brain. So when I look at a neural network like TENN's, for example, I think that it doesn't look anything like a conventional neural network that might be inspired by Huel and Weasel. It's something different. What it does mimic in the brain is this idea of an internal state. So when you look at a conventional neural network, it's usually a feed-forward process. You get an image, you chunk through, and you get your result. But we know for a fact that the human brain doesn't process images that way. Along the way, there's many states which are maintained, which are influenced by the previous history of what you saw. And in a similar way, this TENN's framework captures that internal state in a very nice way, but also in a way that's amenable to using engineering tools and things that we understand. So I think that at the level of abstraction, it captures an essential property of the human brain, of animal brains, which feed-forward networks don't. If we take a feed-forward network and we try to map it into neuromorphic hardware, we're taking away some of the biological inspiration as opposed to adding it. We're taking away the idea that we have internal state where we understand what has gone before and we use that to interpret new data that's coming in. And so just simply mapping like a ResNet 50 to neuromorphic hardware, we're going back in time. This TENN stuff allows us to go to the next step, which is to maintain internal state, much like the human brain, maintain some aspect of the human brain, which is at a different level of abstraction than the biophysics, which was the subject that I think Carver Mead was originally interested in. So it's a new, let's call it a new flavor of neuromorphic engineering. That's how I would look at it. And so what's the future? It's surprising that this technique works so well that we can apply engineering tools to it to control the learning and training so incredibly well, and that we beat out conventional convolutional neural networks, especially at the edge. So right now, I think BrainChip is in an enviable position, being able to run state-space models at the edge. There's maybe one other competitor, Applied Brain Research, with Chris Eliasmith, who's done foundational work in this area as well. But right now, I think we're at the forefront of commercialization. So we have a lead. We have to keep the lead, hopefully. But we think that the world is going to move in our direction. It's going to be very fast where people are going to start implementing state-space models on the edge as well. And so we just hope that we can maintain a lead. And I think we're very proud that we're pioneering this area. I think that's really cool.
Thanks, Sunny. I could clearly feel the cohesion and maturity of this company, and I really liked all of the details and the multiple applications they already have. And for more about BrainChip's work, please go to brainsandmachines.net. And now we welcome back our regular commentator, Professor Ralph Etienne-Cummings from Johns Hopkins University.
Hello, guys. How are you doing? Happy to be back.
Good to see you, Ralph.
So I really would like to start with something that Tony Lewis have said. He said that recurrent neural network, we could do smaller size of classical convolutional neural network. And what I understand is that usually we use convolutional neural networks for spatial data, and then we use recurrent neural network much more for sequential data, for example, language and temporal understanding. So I was wondering if we can explain how you have this shrink in size with recurrent neural networks.
I guess one way to think about it is that if you have some kind of recurrent system, you can actually what's called opening the loop and making a feed-forward version. But when you do so, you typically have to have multiple layers to represent just one loop back because the time constants are different, right? So you need to basically store the partial information that would have happened at different time constants at different points. And then when all those things get summed together, at the end, you get, that is what that one single loop of the recurrence would have done. So in that sense, the network ends up being a much tighter, much smaller network in the recurrent case than in the feed-forward case. Why people like some feed-forward case, on the other hand, is that the data tends to flow a lot faster through it, right? You just get from input to output in a much quicker way, whereas in a recurrent case, there is settling time, right? There's time that it takes for the network to physically settle onto the final value before the results are ready. So temporarily, there might be a bit of a difference in the execution.
There's a big question in my mind as to what flavors of recurrent networks there are. We were talking to Katie Schumann about her hairball networks, which are a kind of recurrent network. But these BrainChip networks are not recurrent in the same way, in that they have to be much more disciplined in the way that they're recurrent, right? There will be a very clear algorithm as to how that recurrence takes place. And I still don't fully understand the difference between the different kinds. But what I would say is it seems obvious that whatever way you're doing recurrence, you are able to cut down on the resources that you're using by essentially using the same resource again and again. Another thing that's confusing is time multiplexing. To what extent is the recurrence that we're talking about time multiplexed recurrent? And to what extent is it just we've got all of these things wired up on the chip?
So I would argue the following. I would say that there's two different types of time multiplexing, if you will, right? You could create an entire feed-forward network with time multiplexing. You're just basically reusing that same neuron to compute partial products along the way. Doesn't imply anything about feedback necessarily. However, in the same sense, I could have mixed and output now with something that happened in the past, and then I've created a loop that then allowed me to essentially create a recurrent net without necessarily physically wiring, right? But you basically temporally wiring. In this case, my understanding was that there was some form of physical interaction, physical loop back. However, because it's digital, it still yet has to have this temporal slicing as well, right? So it just, by its nature, is not like an analog feedback that we can think about.
Exactly. And so if anyone's listening out there, I would love to see a review paper about the different kinds of recurrence that currently exist in different neuromorphic networks. If you know of one, by all means, send it to me.
One quick other thought. I liked the acausal versus causal learning and projection, if you will, and response. I thought that was pretty cool, right? And the example that they gave were nice. Think about the speech to text. You can generate a transcript online, or you can wait till I finish talking and then generate the transcript and get the best, cleanest transcript possible. So if it's not necessary for it to be online, then I would wait, right? But if you're trying to create something where, you're making it a presentation that becomes accessible and folks need the closed caption immediately, then that's an ideal example where you are going to make it as causal as possible, right? Only depend on recent past information. And that is something that the system can do, right? Because they're taking advantage of local edge computation to do that speech-to-text conversion in a causal way. But I do think that the other part about causality and causal learning is that you can also get creativity to come out of it, because you can guess, if you will, on what the next step should be based on only what has happened in the past. I was just talking to somebody about this recently, about the fact that I hear this ad that says hallucination-free AI or something like that, right? And I'm thinking, I want that hallucination because I want it to be creative. I want it to try to give me something that I haven't seen before based on what it's seen in the past, right?
I hallucinate quite enough already without needing my AI to do it for me.
Oh, come on now. You can come up with really cool ideas that you haven't even thought about. Yes, so the other one was, I like the John Tapson piece at the end, because I thought it was a really clear description of how event-based processing can be extended from being single spike, binary values, to spikes with 4 bits, with 8 bits, with 10 bits, whatever the case may be, right? The one thing that I will say is that typically, as this case tends to be, that there are obviously other examples of that payload carrying event, right? Spike-based processing, event-based processing is not limited to a single bit by any means.
Yeah, I love also the dogma that John was referring to. And I think it's up to us now to play around with the interspike interval and trying to understand the spikes on a different way. But there is one question I would like to brainstorm with you on this. So it seems that this Legendre polynomial has been widely used for RNNs, for language models, because you have the history, and then because you have the memory of the conversation to get the context, right? What if you have an abrupt change, continual change of the context?
My understanding is that what's interesting about the Legendre polynomials is not that they provide context in conventional language models, but rather that they encode the way real physical objects behave, right? And he gives the example about things disappearing and reappearing. And of course, physical objects don't do that. And so the whole point is the Legendre polynomials encode a kind of smoothness that physical objects have that language objects would not necessarily have.
Well, it is continuous in the domain from -1 to +1. But the question, I suppose, is how does one stretch that domain to match, for example, a time duration or something to that effect? They are right in saying that Legendre polynomials tend to represent real matter and how matter behaves, even to the electronic level, right? Like the shells of electrons and so on are usually solved in terms of Legendre polynomials and so on. So that's a cool thing. I always appreciate that when you see physics coming in and that becomes part of the computation. I look at them as basically wavelet transforms. You're going to combine them in some ways to create the actual function. Why they are better necessarily than discrete cosine transform or some other wavelet, Dirichlet or whatever, that I don't know that I understand.
I know that they've looked at lots of different kinds of transforms, lots of different polynomials in this particular class, and different ones are useful for different things. So I think they use something different for other kinds of problems. But this whole class has some nice properties.
It seems that they got crazy, insane good results on all of the applications that they talked about. So it would be super interesting for me to look at it. But also they worked on the gesture recognition, which is super interesting for me. But the EVM DVS dataset has the camera stationary. So I would challenge them to use a dataset that actually move the camera and then they do gesture recognitions whilst the camera is also moving, because I'm doing the same and it would be super cool to see how they do it.
On the same front, I'd like to understand a little bit better what exactly was implemented. Was this implemented in purely in algorithmic form, or was it implemented on their hardware? And were they getting the benefits of the hardware in any way, or was this just purely algorithmic? And if I listened to Tony, I thought he was saying that it was on the algorithmic side, but maybe I misunderstood.
And I never was clear about that myself. But altogether, it seems like a very interesting project. And I'll make sure that you can see all of the papers that I got a chance to read in the show notes.
Yep.
So guys, I think this is a great place to stop. And thank you, Sunny, again for a great interview, and Rob for your insightful comments as usual. In the next episode, Sunny will be talking to Jennifer Asler from Georgia Institute of Technology in Atlanta about programmable analog arrays. We hope you will join us then.
That brings another episode of EETimes to its end. Thank you for listening, and thanks again to our guests from BrainChip. EETimes Current is available through all the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find the transcript along with direct links to the other stories we've mentioned and other resources. Thanks for listening.